Hi, my name is Brad Carmen from JuliaHub. This is an addendum to a webinar recorded last year in December entitled Introduction to Modeling Toolkit for Industrial Modelers, which was recorded using Modeling Toolkit version 8 and of course packages as they existed back then and have all been updated quite a bit since then. Most importantly, Modeling Toolkit has been updated to version 9, and with that came some significant and important breaking changes that I will be covering in this video. So the idea here is to cover the code that was generated for that webinar and make important updates where they're needed and discuss why those changes are necessary and what new helpful features exist. So starting from the top, we are going to introduce the software that is needed here. So we're going to be using Modeling Toolkit and differential equations and plots. However, we no longer need to bring in the full suite of differential equations, suite of solvers, because we can now use ordinary diffie-q, a smaller subset of differential equations, which still brings in the feature of having an automatic solver selection. So that saves time on pre-compilation and load time. It's still okay to use differential equations.jl, the full differential equations package. However, if you're doing industrial modeling, likely 90% of your models are going to be ODE problems and nonlinear problems, which are handled by ordinary diffie-q. So the first problem that we solved in the webinar was a steady state problem. There isn't much that needs to change here. We can define our parameters and variables as we did before. We can define our equations as we did before. We still assemble the nonlinear system as we did before and run structurally simplify. However, there is a new feature that we could implement that is called MTK build, which combines these two steps together into one. So instead of having to write 2 lines of code, we can now write 1 line of code. The pros and cons here are that if you are running the 2 lines of code, you can see more information about what's happening. We define 3 equations and 3 variables. It's nice to see that at our first step, we have a system that starts with 3 equations and 3 variables, or unknowns, I should say, which of course is another change that came with Modeling Toolkit version 9. We now call the @variables unknowns rather than states. We can then see when we run structurally simplify that system reduces from 3 equations to 1 equation. If you run MTK build, of course you only have 1 line of code. It's a little bit more straightforward, but you don't get to see that additional information. And in cases when you're trying to figure out a bug with your model, it can be more useful to go ahead and run the 2 steps independently so you can kind of see what's happening. So we can take that system and we can generate a nonlinear problem and we can try to solve it. We see here another change from the previous webinar. We're getting a return code of stalled. And what that is referring to, we can take a look at the residual that we received from that numeric solve, which is 3.7 e to the minus 10. So the reason why we got a stalled is because the tolerance is defaulted to 1 e to the minus 10, and our residual was not able to reach that small. So instead we can change to 1 e to the minus 9, and we get a return code of success. And I would say for this problem, that small of a residual is plenty to give us a useful answer. So we can index our solution like that, and we get exactly the same answer that we had previously. And we can now run a for loop to generate a plot of the orifice size versus velocity limit. We can add here the abstol. This is the one simple change that we might make such that this for loop calculates properly, and we get the same plot that was generated previously. That just shows that we can vary the orifice size, and that will change the velocity limit of our actuator system. Okay, simple enough. So let's move to the dynamic part. Here we have one simple change that we have now with ModelingToolkit v9, which is that we no longer need to define our independent variable and its differential. So instead, we can import them from ModelingToolkit as such. So we have t no units, and we also have t and d that exist as symbols in ModelingToolkit. And the name implies, of course, that t no units is not going to have any units defined. And for this problem, we're going to stick with we're going to make it simple and not apply actual units. Everything is assumed in SI units for this problem. Therefore, using t no units as t and d no units as d is the appropriate thing to do here. So now we can get into solving the dynamic problem using a flat system of equations. This is going to be the incompressible version of this problem. And what I can do is go ahead and execute the code as it was previously. And I can show you that we are going to see an issue when attempting to generate the ODE problem. So that issue is simply that it says that the initialization system is overdetermined. So we have 3 equations for 0 unknowns. Essentially what it's saying here is that we have 3 additional constraints for our initialization. So that's new. That is not what we had in version 8. And I can show you exactly why we're getting that. So the over-constraining of this initialization problem is coming from our definition of our variables that we did here. Each one of these equals signs is creating a default in ModelingToolkit terms, but that also means it's creating an initial equation for each of these variables. And since we're defining 5 variables and each one of them has an initial equation, ModelingToolkit is telling us that that's actually too much information. We're actually over-constraining this problem. So the way we're going to fix that is to rewrite these in a new form. So I'm going to copy some code to save some time here of the way that we would write this properly using a begin and end block. And what I have here is a new nomenclature where we can assign each of these values as a guess. So this is a very important distinction. So if we use the guess keyword, then we're not giving an initial equation, we're just giving a starting point for the solver to find what the initial value of each of these states or unknowns should be for this problem. So let's go ahead and run this again, and let's see what it says now. So now we get an error, and the error says that the initialization is incomplete. And it's complaining about the x variable. Now, this information is not very complete here. I'm going to show you now what code we could use to dig a little bit deeper and try to make a little bit more sense about why the initialization is incomplete. So I'm going to copy some more code over that is useful code for figuring out what the heck is going on when you get this error. So a new function that exists in V9 is this generate initialization system. So these lines of code are what are being executed under the hood when we build an ODE problem. And if we generate this initialization system and take a look, you'll see here that we have 3 equations, 5 unknowns. And now we have a bit more information. We can see that we are actually we're missing 2 unknowns, or 2 equations, I should say. So how do we add these equations? So there's 2 different ways we can go about adding these equations. And what should these equations be? So one way we can know what initialization equations we should be using or adding is to count how many differentials we have. So we see that we have 2 differentials, so therefore we're probably going to need to give 2 initialization equations. And it's easiest to think about the states or the unknowns that are being differentiated. So easiest here is if we're just going to give the initial values for x and x dot at time 0. However, we're not limited to that. We could give 2 initialization equations for any of these 5 unknowns. But for this problem, I think it's easiest to think about it in terms of the 2 differentials that we have here. We want to start this problem where x is at 0 and the velocity is at 0. So we're starting at rest. We're starting at a neutral point. Simple enough. So there, as I said, there's 2 different ways we can give that information. One is to give the initialization equations as a keyword. So we could say we want x at 0 and we want x dot at 0. And we can provide that keyword in several different places. We can provide it at the ODE system level, or we can provide it at the generate initialization system level, or we could provide it at the nonlinear problem level. So let's go ahead and just do it like this at this level, and we can see now we have 5 equations and 5 unknowns. Okay, very cool. So then we can go ahead and run structural simplify. We can build the nonlinear problem and solve it, and it solves successfully. And what that means is that we can now generate or pull the initial values for any of these 5 states, or unknowns, I should say. So it's easy enough to build a U0 vector like this, and then we can apply that U0 here, and we can easily build the ODE problem. Or, as I said, I am simply showing what's happening under the hood here. We could simply apply the initialization equations as a keyword here, and we can get the ODE problem built with all this code executed under the code for free. And as you can see, we still get the ODE problem generated with no errors now. Now there's one more way you can go about this, which is that we can generate those initial equations at the variable definition level. So we could just say that x is equal to 0 and x dot is equal to 0. And when we do it this way, when we generate the ODE system, this now contains these initial equations inside the ODE system. So when we come here to the ODE problem with that system and generate it, it's also happy that way as well, right? We can also see that here if we want to look under the hood. So we're going to get rid of the initialization equations. They are now defined in the system itself. And when we look at that, we can see we have 5 equations and 5 unknowns. Everything's in balance. Okay, very good. So we can solve it, and we can see that we are getting still the same result that we had before. All very good and easy. So now let's move to the component-based section. We're going to want to apply the same concept of removing initialization equations at the component level, because we are going to easily overconstrain our problem if we're going to be defining initial equations like we are here at the very low level. So here we're defining a connector. We do not want to specify initial equations at the connector level unless we very specifically would like that to be the case. In general, we're never going to want to do that. So instead, we're going to want to define a guess for each of our unknowns. And setting it to 0 is a fine guess. In some cases, it may make sense to provide a value that you would have a bit more information, but for this case, a connector, we don't know any information about what this is being connected to, how it's being used. It's a very generic component, so we just guess at 0. So we have a port for the hydraulics, and we have a flange for the mechanical parts. Same philosophy. Everything should just be guessed at 0. Okay. Now, we're going to continue to apply that philosophy as we go through each of the components. So let's do that real quick. We have the orifice component. We can remove this P prime because we don't need it anymore for our defaults. So previously we were doing a lot of hard work here to default all unknowns, all variables. We're brute forcing it, right? We were making sure that all unknowns were being set to a proper initial default value. We no longer need to do that. ModelingToolkit is going to solve all this information for us. Based on whatever boundary conditions we give the problem, it should be able to propagate those boundary conditions throughout the problem and figure out what all the states should be initialized to. So it's a very cool feature. It allows us to write much cleaner code for our components. So instead of specifying exactly what the pressure should be, we simply need to specify a guess. And just like I was saying about the components, we don't really know how this orifice is going to be used, so it's hard to say what the guess should be. We can just guess at 0. That's fine. Perfectly fine. Okay, now there's one more very important lesson to be taught here about the orifice component. So in the past, in my evolution with ModelingToolkit and learning how to be a better modeling engineer, it's become clear that there is something going on with these equations that is not ideal or not optimal. There's actually two things going on with this equation that are not good. So the first thing that's happening here is that we're trying to build a generic component, an orifice that has a pressure on either side of the orifice, and we have a flow variable that we're not constraining what direction that flow goes through this orifice. It can go left to right from P1 to P2, or it could go the other way, P2 to P1. If it goes from P1 to P2, you would expect P1 to be greater than P2. And flow always goes from higher pressure to lower pressure, of course. However, if that was the opposite case, if it's going from P2 to P1, and P2 is greater than P1, then you would expect, of course, this left-hand side of the equation to be negative. And if this is negative, and the flow is going in the negative direction and the flow is negative, then you would expect the right-hand side to also be negative. But we can see that U is linearly related to mass flow m dot. That means if m dot is negative, U is negative. But if we square it, we get a positive value. And therefore, we'll have a negative on the left-hand side and a positive on the right-hand side, and that's no good. So whenever we square a value, we need to, or take the square root of a value, we need to be very careful about the sign. So there's one way to solve this, which is to use the sign function. That would ensure that if u is negative, that the right-hand side of the equation would be negative. We could also write that u times absolute value of u. That would also effectively give us the same thing. And that's all fine. However, this still has one more issue, which is that a square or a square root of something gives either a zero differential. So when we're squaring something at zero, the derivative is zero. And for a solver that is using gradient descent, such as Newton iterations, that becomes very problematic because there is no longer any descent if your derivative is zero. So there is a fix to that problem, which is to define a new function for how a variable is squared. So I'm going to copy some code in here that will provide us some better understanding. So this is a classic solution to this problem. This formula approximates a square or a power of x. And we can take a look at what that looks like. So if we plot this function compared to plotting just the pure square of a value, we can see that the blue line, which is the reg_pow, is giving us a very similar result to a square of a value. They're essentially line on line. And we can see that the sign issue is solved here. So this is a signed square. So that's good. That solves that problem. So what is the difference? So if we zoom in, we can see that actually there's a very significant difference here. The derivative is no longer zero at zero. So this is really going to help the solver out whenever we're using any kind of gradient descent. Now we have a gradient. And that's going to allow us to go from a stalled solution to, or a diverging solution to a successful solve. Okay, so let's go ahead and implement that change. So this is going to be reg_pow of x squared. There we go. So now we have both the sign change, sign is fixed, and the derivative at zero is fixed. Okay, so there is our orifice component. Now we can go ahead and fix the volume component. And I am going to implement essentially this important fix. We're going to make sure that this problem is not over-defined with its variable definition. However, as you can see, I'm going to leave x defined because the volume component, by its design, we need to provide what is the volume at time zero. So this is actually necessary information. So whenever you have a condition where you're designing a component and one of the variables does need to be specified at time zero explicitly, then that's fine. Then this is how you should define your component. So here we have a parameter that is specifying what is x at time zero, and we go ahead and assign it and create that initial equation. That's perfectly fine. That's exactly what we ought to be doing here. Everything else, nothing else we know. We don't know what the pressure is, the mass flow, the density, everything else we just guess at zero. Okay, so we can remove also this additional information that we were providing previously to fully constrain the problem. We no longer need to do that. That's all given to us for free now. Okay, so I'm simply going to continue to follow that pattern here. We'll update the mass component and remove this extra information. And finally, the actuator component, same philosophy, same pattern. We're just removing extra information we no longer need anymore. Okay, so all of those can be simply defined now rather than over-constrained. And we have just our source left, our damper, and we finally get to our system. So here we can only need to provide information about the pressures. So you can see we were providing the pressure information at every component before. Now we only need to specify it at the source, at the boundaries of the problem, essentially. And we can see now that when we generate the system, oh, I must have made a mistake somewhere. Let's just make sure I execute everything here. Okay, so okay, I must have, okay, we're getting an error here, which means I must have, aha, I intended to put u here, not x. U is the actual variable that I'm trying to square. My apologies. But it's good to see that. Okay, so here we are. We're getting this error again, initialization incomplete. So we should go ahead and take a look at under the hood and see what the heck is happening. So we can copy some code in here. And what I have here are some initialization equations that I know I'm going to need, but let's start without them because let's pretend that we are trying to figure out what they ought to be. So if we take a look here at the initialization system, we can see that we have 50 equations and 54 unknowns. So we're missing 4 extra initial equations. That's what this really helps us learn and see. So what are those 4 that we ought to have? So if we look at the equations of the system, we can see we have 6 differentials. And so that is a good clue, right? We want to look at those to see how many initial equations do we need and what variables it would be a good starting point to think about assigning initial equations to. So just as we kind of did before, these two kind of are similar to what we did in the incompressible problem. We said the position of the actuator should start at 0 and the velocity should start at 0. So that's a couple that are pretty obvious. And then one other question that comes to mind is we have 6 here, but we have, when we look at the initialization system, it says we need 4. So why do we have only 4 needed when we actually need 6? Well, that is because the volume position, x, already has an initial equation. We have actually already assigned that. So just as a reminder, that was the one initial equation that we created in our system. So that's already been decided. And since we have 2 volumes to create an actuator, we have created 2 initial equations. So that's why we just need 4 left. Okay, so as I said, it makes sense to define the initial position and velocity of the mass. And now we just need 2 more. And as we can see, if we look at what's left, we have the density of each of the volumes are the final pieces that are a good idea to provide an initial equation for. However, density is kind of a little tricky. Density is a function of pressure. We'd have to actually do some math to figure out what that ought to be. So what we could do instead is, what we do know is what the pressure should be in each of those volumes. So we can, instead of providing density, we could actually just provide pressure, because we actually could provide any state that we want. Our system has 10 states, or actually you could say our system actually has, let's see how many we start with, has 54 unknowns. So we could actually provide initial equations for any of those 54. But to keep things simple, let's just focus on what our equations are telling us. So let's provide the pressure for the 2 volumes. That is information that we know, and so now we have all 4 initial equations. So let's go ahead and add that information here to our initialization system, and you can see we have 54 equations, 54 unknowns. Perfect. And when we go to simplify it, now it should be working. However, I have failed to execute this all in order, so let me do that again. So here you can see we have a nice balanced system, 4 equations, 4 unknowns. So we can go ahead and assemble the initial problem. We remember to set t to 0, and we can solve it. And so now we can see that we can easily build our u0 vector, and here we can see that we got our densities solved for us, which is very cool. And we can use that by either specifying u0 here, and we can now build our problem without an error, or we could, of course, specify our initial equations here as a keyword, and that also works. Okay, so one final note. So previously, we attempted to solve the problem with implicit Euler, giving some additional keywords for the nonlinear solve because we're having trouble solving this problem. And that was exactly the issue with the square of the flow. That was what was causing that issue. And it can still be solved. It is possible to brute force the solve by using a nonlinear solve with the divergence turned off and to do non-adaptive. However, that means you're not getting a very efficient solve. You don't have it error bounded, and you're using a lower order solver. So it might be much better if we get adaptive solving, and if we could just have a higher order solve as well for a much lower error. So let's go ahead and try now if we can solve this with RODAS5P without specifying any special conditions. As you can see, a success is there. So we now have a nice clean way to solve this problem. And as you can see, with the compressible model, we get this very dynamic solution because essentially that oil is acting as very stiff springs. But over time, we arrive at that same exact velocity, 1 meter per second, which is what we got in the incompressible solution. Okay, very good. Thank you very much for watching this webinar, and I hope you learned a lot.